Good morning. Today we're going to talk about some special things that can happen with systems, some sort of unique situations. We've been solving systems for a long time. We've talked about solving them with graphs. We've talked about solving them with substitution, with elimination. These are still the same kind of systems, but now we're talking about, again, some of the unique things that can happen when you're solving a system. And I know one of these things you saw in one of your homework assignments already. So first, just some vocabulary, and I'm just going to pause here for a second, give you a minute to copy these words down. If I don't give you enough time, you may just want to pause the video and copy them down yourself. There's two ways we classify systems. We classify them as being consistent or inconsistent, and then we classify them as being independent or dependent. So every system gets classified two ways. Consistent means the system has a solution. And remember, the solution is the point where the two lines cross. So if when you graph your system, the lines intersect somewhere, that means that system has a solution. I'm really fumbling on those words today. The system has a solution, and therefore we would call it a consistent system. Inconsistent means there's no solution, and the only way you can get no solution is if the lines do not intersect. And what I wanted you to think about from geometry is if the lines do not intersect, that means they must be parallel. Okay, so parallel lines would result in an inconsistent system. Then we also have independent and dependent. Independent means your system or your two equations make two completely separate lines. Okay, dependent means it's two different equations, but when you graph them, they actually end up being the exact same line, and that happens sometimes too. So that's the difference between independent and dependent. So in terms of graphs, in terms of looking at a system on a graph, one of these three things is going to happen every time you graph systems. Either you're going to have two lines that cross, and this is where majority of our problems have fallen. Just about every one we've done has been two separate lines, and you were just looking for the place where they cross. But it's also possible that your two lines are parallel to each other, and it's also possible that the two lines, as I said a minute ago, lie right on top of one another. So let's talk about how these would be classified. This first one that we like so much does have a solution. The solution is right here. This is the place where the lines intersect. So we would call this a consistent system. Okay, consistent again means there is a solution somewhere. Now here, this one, there is no place where the lines cross, so there is no solution to the system. And remember, the solution to the system is the one point that the two lines share in common. So that's what I mean when I say no solution, is that the points or the lines have no points in common. Now this one is a little bit different than what you're used to thinking about. But remember, consistent means the lines have a point in common, and inconsistent means the lines do not have a point in common. And on something like this, the lines have all of their points in common. Okay, so every point on this line would be considered a solution. I would call this a consistent system. Next, we have to look at whether they're independent or dependent. And remember, independent means it's two different lines. Dependent would be something like this, where the two lines are actually the same line. So this one, because I've got this line and this line, two separate lines, we would call that independent. Now this one here is kind of an anomaly, because if I were making the rules and I were looking at my definitions of independent and dependent, I would definitely call this independent because you've got two separate lines. But for whatever reason, if the system is inconsistent, meaning it doesn't have a solution, the lines are parallel, we don't classify whether it's dependent or independent, anything at all. We just say it's inconsistent, and that's enough said. Okay? So that one you don't really have to worry about. And then this one, because these two lines are really the same line lying on top of one another, we would call it dependent. Okay? So If it's consistent and independent, that's, again, this is majority of the systems you're used to. Almost every problem you do, if you can find a solution to it, it must be consistent and independent. That's going to have one solution. I'm going to have to slide this up a little. If it's inconsistent, that means the lines don't cross anywhere. Okay, so that means there's no solution, because that solution would be the place where the two lines cross. Okay, so we would say no solution. And then finally, if it's consistent but dependent, meaning the two lines are really the same line, remember, you're looking for the point that they have in common. These lines have every single point on them in common. It's not every point everywhere, but it's every point on those two lines. And those lines go on forever. So that's a whole lot of solutions. So we have infinitely many solutions, because, again, those lines go on forever, and every point on the line would be considered to be a solution. Okay. So this is just to wrap your head around some vocabulary. There are going to be some questions on your homework where you're asked to classify, like, what kind of system is this? But I wanted you to see what they would look like on a graph, and then we'll talk about solving them. Now, sometimes the equations are just written in a way to where you can look at them and know right away, right, without having to do any sort of solving, whether they're going to be no solution or infinitely many solutions, or whether they're going to have a solution. So if the graphs are written in slope-intercept form, and remember that's y equals mx plus b, if they're written that way, if they're written in slope-intercept form, they're going to be no solution if they have the same slope but a different y-intercept. Because remember, that same slope implies that the lines are parallel. Okay, and so there will be no solution. So if you're looking at two equations, and this is going to erase in a minute when I flip the slide, but if you have like y equals 2x plus 5 and y equals 2x minus 7, let's say, I know just from looking at those that those lines are going to be parallel. And as soon as I know that they're parallel, I know I don't have a solution. So I don't even have to solve anything. I can just say no solution. Now, sometimes they're a little sneakier than that. Sometimes they write one of them in slope-intercept form and one of them in a different form, and then you've got some work to do. But just a quick way, if you catch it, great, that saves you some work. On the flip side to that, they would be infinitely many solutions if they still had the same slope, but this time their y-intercept would have to be the same as well. Because remember, this infinitely many solutions comes up when they're really the same line, one on top of the other. Let's talk about if they're written in standard. In standard form, it would be a no solution if the a and b values were the same, but the c values were different. So if you had 2x plus 3y equals 10 and 2x plus 3y equals 4, let's say. Those are going to have the same slope because they have the same a and b value, but they have different c values, which means they're going to have different intercepts. So it's kind of the same thing as this. Okay. Again, these are kind of tough to come by because a lot of the times it's not that obvious. A lot of the times one of the equations is not written in that form or you don't recognize it right away. So these are some shortcuts for you, but I would not waste a lot of memory space memorizing this. It's just more of a, if you happen to notice this in a problem, you can save yourself the work. And you would have infinitely many solutions. Again, remember that means they're really the same line if the a, b, and c values were all exactly the same. Okay. The last page in your notes for this lesson, I don't have a copy of it here on the slide, but it says Reteach 6-4, Solving Special Systems, and I just want to run through the 3 examples at the bottom so you can sort of see what happens when one of these comes up. So the first example says y equals 3x and 2y equals 6x. Now, if I were being asked to solve that, I would probably want to use substitution because it's already set up with y equals. I know that y is equal to 3x. So I can plug 3x in for y really easily. Okay, and that's going to give me 2 times 3x equals 6x. Well, 2 times 3x is just 6x, so 6x equals 6x. Now, you may remember from when we did equation solving originally that when you end up with an equation where the two sides are exactly the same, the answer is going to be all real numbers. That's similar to systems, except we don't say all real numbers because your solutions aren't just numbers, they're coordinates. This would be one of your infinitely many solutions. Let's say you didn't know that for sure. What I would probably do is subtract 6x from each side. And then you're going to end up with 0 equals 0. So anytime these numbers end up exactly the same, and again, I could have caught it back here when the 6x's were exactly the same. Anytime you have two things that are exactly the same and everything else is canceled out, that's going to be infinitely many solutions. Again, similar to the all real numbers from back when we were equation solving, but we say it a little differently with systems. Okay, let's look at the next one. The next one says y equals 2x plus 5. So again, you should be writing these down on the last page. This is the very last page in the whole packet. It says reteach 6.4. And y minus 2x equals 1. Okay, again, this is set up really nicely for substitution. So I'm going to take what y is equal to, plug it in right here for y, and that's going to look like this. 2x plus 5 minus 2x equals 1. Well, when I go to simplify, I've got 2x minus 2x, so those cancel out right now, and I'm left with a 5 here and a 1 here. Okay? That's different than what we had up here. Up here we had two of the exact same number. Here we have 5 equals 1. That's not a true statement. Anytime you end up with two different numbers, that's going to be a no solution. That's going to be one of the ones where the lines would be parallel. If we went back and graphed these two, we would find that they were parallel lines. Okay? And let's take a look at the third one. Number 3 says 3x minus 2y equals 9, and negative 6x plus 4y equals 1. Okay, this one's set up to where elimination would probably work the best, because I don't have a y equals set up really nicely, but I do have all the variables lined up. So if I focus on my x's, and I want those to cancel out, I would really love for this to be a positive 6 to cancel with that negative 6. So let's multiply the top equation by 2. Okay? And so now I have 6x minus 4y equals 18. So now when I go to solve, watch what happens. I was trying to get the x's to cancel, so I know those are going to cancel. But look what happens to the y. In the y values, those cancel also. So I'm left with a big fat 0 over here. And on this side, 1 plus 18 is 19. Okay? So again, that's the same as this situation back here. I ended up with two different numbers. So that's also going to be a no solution. Now what happens sometimes with elimination is if I had done all of this, and this had canceled, and this had canceled, and this had also canceled, if these had been like a positive 1 and a negative 1, if it had worked out that way, then I would have 0 equals 0 here, and then that would be the same thing as the infinitely many solutions. So I wanted you to see what these look like when you're actually solving them. There was one on last Friday's homework assignment that was a no solution problem. I believe it was number 13, and a lot of you caught that as you were doing it, that it works out to be no solution. So nice job with that. Okay, well, we will touch base on this some more tomorrow. Again, I would not spend a whole lot of time on trying to figure out without doing the work, like, is this no solution? Is it infinitely many? A lot of the times you're going to have to solve it like you normally would, and then at the end, you look at what you get and you decide infinitely many or no solution. But I would practice that vocabulary back at the beginning, okay, because there will be questions on your test that ask you things like, is this system consistent or inconsistent, or things like that. So practice that vocab. But otherwise, that's it for today.